Hi, everyone! Welcome to the 5th episode of the video series about evolution from traditional VPN to eVPN. This episode focuses on how to evolve from traditional HoVPN to SRv6 HoVPN. Evolution from traditional IP RAN HoVPN to SRv6 HoVPN can be classified into the following types. Evolution from L3 VPN over MPLS to L3 VPN over SRv6. Evolution from L3 VPN over MPLS to eVPN over SRv6. This video uses the evolution from L3 VPN over MPLS to eVPN over SRv6 as an example to describe the detailed evolution process for this scenario. Using this typical networking as an example, the network is divided into three areas: access, aggregation, and core. RR1, which is also a P device, serves as the RR for the aggregation ring, while RR2 serves as the RR on the core side. Before the evolution, MPLS tunnels are used to carry L3 VPN services. BGP VPN v4 peer relationships are established between ACCs and AGGs, between AGGs and RR1, between RR1 and RR2, and between RR2 and PEs. After the evolution, it is expected that SRv6 tunnels be used to carry eVPN L3 VPN private line services, and BGP VPN peer relationships be established between ACCs and AGGs, between AGGs and RR1, between RR1 and RR2, and between RR2 and PEs. The overall evolution roadmap is as follows. Phase 1, evolve and upgrade the aggregation ring. Phase 2, evolve and upgrade the access ring. After network-wide evolution is complete, delete the root reorigination configuration. Next, let's take a look at the specific evolution steps. Phase 1, evolve and upgrade the aggregation ring. First, enable SRv6 globally and configure SRv6 locators. Second, configure basic ISV6 functions and BFD for IGP. Third, configure priority-based route selection for a BGP VPN instance. Fourth, configure BGP. Fifth, configure IPv4 eVPN, L3 VPN. Sixth, configure AGGs to advertise VPN static routes. Seventh, configure BGP IPv6 related route selection. First, enable SRv6 globally, and configure SRv6 locators on AGGs, MCs, and RRs. This video uses the master AGG, AGG3 as an example. SRv6 needs to be globally enabled first. Then advertise SRv6 locators in IS processes to enable SRv6B. In addition, enable TLFA in IPv6 FRR. To meet the reliability requirements of network services, fast link switching is required in the event of an IS fault. Remote LFA allows traffic to be quickly switched to a backup link before route convergence is complete in the control plane, preventing traffic interruption. The configurations of the backup AGG, AGG4, MC1, MC2, RR1, and RR2 are similar to those of AGG3, and so are omitted here. Next, configure ISV6 in the aggregation ring IGP processes of AGGs and MCs. The coexistence of ISV6 and IPv4 does not affect live network services. This video uses the master AGG, AGG3 as an example. On each involved interface, enable IPv6 forwarding, configure an IPv6 address, and enable ISV6. The configurations of the backup AGG, AGG4, MC1, MC2, RR1, and RR2 are similar to those of AGG3, and so are omitted here. Next, let's check the SRv6 configuration. Here, AGG3 is used as an example. Run the display ISIS peer command to check is neighbor information. Neighbor information is displayed if neighbor relationships have been set up successfully. The command output shows that the state field is up on RR1 and AGG4, indicating that AGG3 has established SRv6 neighbor relationships with RR1 and AGG4. Run the display ISIS interface command to check information about the ISIS interface on AGG3. To prevent EVPN routes from affecting original VPN v4 routes after EVPN is deployed, configure a high priority for VPN v4 routes on nodes with VPN instances before deploying EVPN. This ensures that VPN v4 routes are preferentially selected before SRv6 is deployed in an E2E manner. This video uses AGG3 as an example. The configurations of the backup AGG, AGG4, P1, and P2 are similar to that of AGG3, and so are omitted here. Next, configure BGP. Configure MPI BGP for upstream route evolution required by upstream service traffic. This video uses AGG3 as an example. Configure route policies. Configure MPI BGP. Configure AGG3 to re-originate routes learned from ACCs in the BGP VPN v4 address family and advertise re-originated routes to RRs from the EVPN address family. The following uses configuring MPI BGP for upstream route evolution on AGG3 as an example. The configurations of AGG4, RR1, RR2, P1, and P2 are similar to that of AGG3, and so are omitted here. Next, let's configure MPI BGP for downstream route evolution. This video uses AGG3 as an example. It re-originates routes received from the RR in the BGP VPN address family and sends re-originated routes to ACCs from the VPN v4 address family. The configuration of the backup AGG, AGG4 is similar to that of the master AGG, AGG3, and so is omitted here. Then, run the display BGP VPN peer command on AGG3 to check the BGP VPN configuration. The command output shows that the state field is established, indicating that the BGP EVPN peer relationship between AGG3 and RR1 has been established. Fifth, configure IPv4 EVPN, L3 VPN. The configuration procedure is as follows. First, configure L3 VPN instances on the live network. Second, configure VPN prefix route advertisement. This video uses IPv4 EVPN, L3 VPN on AGG3 as an example. The configurations of AGG4, P1, and P2 are similar to that of AGG3, and so are omitted here. Run the display IP routing table VPN instance for ground command on AGGs and PEs. The command output shows that upstream and downstream routes on the aggregation ring have recurs to SRv6 B tunnels. Run the display BGP VPN all routing table prefix route command on AGG3 to check whether ACC side service routes have been re-originated. The fields in red in the command output indicate that the routes have been re-originated in the EVPN address family and re-originated routes have been sent to ACC1 and ACC2 from the VPN v4 address family. To prevent black hole routes on AGGs, configure VPN static routes on AGGs, and set the next hops of the routes to the loopback interfaces of MCs. Ensure that the addresses of the loopback interfaces on the master and backup PEs are the same, so that the performance of static route switching can be guaranteed. In SRv6 tunnel scenarios, you need to enable static routes to recurse to SRv6 tunnels. First, configure the VPN default route. Second, advertise the VPN default route. Configure VPN static route advertisement on AGGs. This video uses AGG3 as an example. The configuration of AGG4 is similar to that of AGG3, and so are omitted here. In the BGP-VPN instance view, configure the device to prefer IPv6 peer routes for tunnel switching, so that services can evolve to be carried over SRv6 tunnels. This video uses configuring EVPN route selection on AGG3 as an example. The configurations of AGG4, P1, and P2 are similar to that of AGG3, and so are omitted here. Run the display BGP-VPN v4 VPN instance routing table command on AGG3 to check the route advertisement result of P1. The command output shows that IPv6 routes are preferred. At this point, all services on the aggregation and core rings have evolved to EVPN over SRv6. Phase 2. Evolve and upgrade the access ring. This involves the following 6 steps. First, enable SRv6 globally, and configure SRv6 locators on ACCs and AGGs. The overall configuration procedure is similar to that for aggregation ring evolution, and so is omitted here. Then, configure SRv6 in the access ring IGP processes of ACCs and AGGs. SRv6 and IGP IPv4 coexist in this scenario. The overall configuration procedure is similar to that for aggregation ring evolution, and so is omitted here. Check the SRv6 configuration result. Run the display ISIS peer command on AGG3. The command output shows that the state field is up for a CC1 and a GG4 in IS process 1 access ring, meaning that AGG3 has successfully established SRv6 peer relationships with ACC1 and AGG4. The state field is also up for RR1, AGG4, and MC1 in IS process 100 aggregation ring, meaning that AGG3 has successfully established SRv6 peer relationships with RR1, AGG4, and MC1. Next, configure priority-based route selection for BGP-VPN instances on ACCs. The overall configuration procedure is similar to that for aggregation ring evolution, and so is omitted here. Next, configure BGP. This video uses ACC1 as an example. The configurations of the ACC2, AGG3, and AGG4 are similar to that of ACC1, and so are omitted here. Then, run the display BGP-VPN peer command on ACC1 to check the BGP-VPN configuration. The command output shows that the state field is established, indicating that BGP-VPN peer relationships between ACC1 and AGG3 and between ACC1 and AGG4 have been established. Fifth, Configure IPv4 EVPN L3 VPN. The overall configuration procedure is similar to that for aggregation ring evolution, and so is omitted here. Run the display BGP-EVPN all routing table prefix route command on ACC1 to check whether ACC1 has correctly learned the EVPN default route advertised by the VPN instance. In the BGP-VPN instance view, configure the device to prefer IPv6 peer routes for tunnel switching, so that services can evolve to be carried over SRv6 tunnels. This video uses configuring EVPN route selection on ACC1 as an example. The configuration of ACC2 is similar to that of ACC1, and so is omitted here. Run the display BGP VPN v4 VPN instance routing table command on ACC1 to check the route advertisement result of ACC2. The command output shows that IPv6 routes are preferred. At this point, all services on the live network have evolved to EVPN over SRv6. You can delete L3 VPN over MPLS configurations from the access ring in this case. If the access ring connected to the aggregation ring is not upgraded, the L3 VPN over MPLS configurations cannot be completely deleted. The deletion operation must be performed after the entire network is upgraded. After the L3 VPN over MPLS configurations are deleted from the access ring, EVPN routes on the access ring need to be re-advertised to the L3 VPN on the core and aggregation rings. If the core and aggregation layers are completely reconstructed, but some access rings remain unreconstructed, configure L3 VPN to EVPN route reorigination. If the core and aggregation layers are not completely reconstructed, you need to configure EVPN to L3 VPN route reorigination. Step 1. Delete the upstream route reorigination configuration for the aggregation ring. This video uses AGG3 as an example. Disable AGGs from reoriginating routes learned from ACCs in the BGP VPN v4 address family and then advertising reoriginated routes to RRs from the EVPN address family. The configuration of AGG4 is similar to that of AGG3, and so is omitted here. Step 2. Delete the downstream route reorigination configuration for the aggregation ring. This video uses AGG3 as an example. Disable AGGs from reoriginating routes learned from RR1 in the BGP VPN address family and then advertising reoriginated routes to ACCs from the VPN v4 address family. The configuration of AGG4 is similar to that of AGG3, and so is omitted here. After all the preceding configurations are complete, the evolution from traditional HoVPN to SRv6 HoVPN is complete, and all services have been switched from L3 VPN over MPLS to EVPN over SRv6. That's all for this video. Thank you for watching.